Hi guys, we're going to continue our work in probability today. We're talking about compound events. Compound events are just when we have more than one event that has been combined together to make up our sample space. And we're going to have a look at what we call independent versus dependent events. So we're going to have a look at some independent ones first. Just a reminder that independent events are events where the occurrence of one event does not affect the occurrence of another. So let's have a think about, the good old traditional two coins being tossed. So let's have a look. When we have two coins tossed, let's have a look at what a tree diagram looks like. So here is our first coin. So we can have a head and a tail. Remember that each branch on a tree diagram represents one of the outcomes. We've got two outcomes here, head or a tail. If we get a head on the first outcome, does that affect what we get on the second? No, of course it doesn't. So let's have a look there. So if we get a head on the first, we can have a head on the second or a tail on the second. What about if we had a tail first? Well, of course that does not affect what we get on the second one, so we could have a head and a tail. So here is our sample space. I was going to put SS for sample space. Reading along the branches to get our sample space, we've got head, 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 tail, or a tail then a head, or a tail then a tail. So we've got four outcomes in our sample space. Now, each of these has exactly the same chance of outcome here. So we know the probability of getting a head, head is 1 in 4. Getting a head then a tail is 1 out of 4. Tail then a head's 1 out of 4. Tail then a tail is 1 out of 4. Okay, that's pretty straightforward, simple. So if we were asked for something like this, probability of a head and a tail together. So we look at our sample space here and say, okay, head and a tail means I could have this outcome here, or I could have this one here. So I'm just going to come over here and say that really means I can have a head, tail, or probably of a tail then a head. Okay, so what does intuition tell you here? You know very well that we've got 2 out of the 4 outcomes. We know the probability of getting head, tail, or a tail heads 1, 2 out of the total of 4. Or what we could do, probability of getting a head, tail is 1 out of 4. Or probability of tail, head is 1 out of 4 also. But we know the probability is a half. We knew we had 2 outcomes out of 4. So this or really means we're adding the separate probabilities. So if we want 1 or more outcomes in this sample space, we can add the probabilities. So we can have 1/4 plus the 1/4 is our 2/4. Okay, another little observation we're going to have a look at here. Alright, if I go back to my individual branches and I say, well, in the first toss, the probability that I get a head is 1 out of half. So I'm going to write that down there. The probability that I get a tail is also 1 out of half. We say they're equally likely outcomes. Alright, and since getting a head does not affect the second toss, then I know I have a half chance of getting a head on the second and also a half chance of getting a tail. And similarly down here. Another little observation you might want to make, if I come over here and said, what is the probability of getting 2 tails together? Well, if we go to our sample space, we know that it's 1 in 4. There's our 2 tails. But if we have a look at if we come over here at our 2 tails, another observation you make, that if we have probability of a tail for the first toss and a probability of a tail for the second toss, which is of course 1/2 and 1/2. What math do we actually have to do to make 1/4 there? Well, we actually have to multiply those together. So if we want one of these outcomes in the sample space, we know that we can actually multiply the probability along those branches. Alright, so let's write down what we've just noticed there. So if A and B are independent events. And the first thing we know is if we want probability of A and B, like this one here where we wanted a tail and a tail, we know that we can multiply those individual probabilities times probability of B. And another observation that we can make, if we want more than one outcome, then we can add those probabilities. So even though it's a bit difficult here, if we want probability, for example, A or B, where A and B are independent, just like head, head, and tail, tail. So if we wanted the same outcome, so both heads or both tails, we can have head, head, or tail, tail. And we know that we can add those. So we have the probability of A plus the probability of B. These are our keywords, and or. We remember we associate with multiplication and the addition there. Alright, so that's pretty straightforward. Let's actually go and have a look at one where you'd actually need this a little bit more than you perhaps would with that nice simple one. Okay, so we've got in a bag, sorry for my lack of creativity here, there are 3 red and 2 blue blocks. One block is drawn, replaced, then another drawn. Okay, so we've got a compound event with 2 events happening. So let's have a look at our first draw. Alright, we have 2 red and 3 blue. So let's write those down. In my first draw I could have a red, or I could have my 3 blue. So blue, blue, oh this is getting tedious already, blue, blue, blue. Alright, now let's go and have a look at what our second draw would be. Since we replace the block, does what we get on the first draw have any effect on our second draw? No, it doesn't. So if we got a red on the first draw, but we did put it back, we still have the 2 reds to draw in our second one. So for this outcome, I have a red, red, as well as these 3 blues. Oh, let me get my blue. Blue, blue, blue. Alright, we'd have exactly the same for this one down here. Getting a little bit crowded. Let's go to the blue here. Alright, if we had a blue on the first draw, once again, and we put it back, has no effect on the second. So we have a red and a red. And of course we could also then have the 3 blues. So I could have a blue, blue. Oh my goodness, look at that. So here we've got how many outcomes? 5 there, 5 there. And how many of those branches would we have? We'd have 1, 2, 3, 4, 5. So if we were to go and list our sample space, we would have 5 lots of 5. We'd actually have 25 outcomes in our sample space, which is quite a lot, and a bit tedious to have to do it with this. Okay, but you could go and start listing. So we could have red, 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 blue, red, blue, red, blue, and you'd have the same again. You'd have red, 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 blue, red, blue, red, blue, and you'd have that 5 times, and you get your 25 outcomes. Now, as you can see there's an awful lot of repetition. Well, I don't like doing things where it takes me a long time, so we can actually modify our tree diagram. Now that we know about this multiplication principle, let's have a look at another alternative, which is going to be definitely a lot nicer, I think. All right, so let's go back and have a look at our first draw. So instead of putting a branch for every single outcome, all 5 outcomes, we're just going to put a branch for the different outcomes. We've got reds and blues. So let me put my branch here. I can either get a red on the first one, or I can get a blue. Now, are these equally likely outcomes? No, they're definitely not. There's definitely more chance of getting a blue. So what I'm going to do, I'm going to write the probability of getting a blue. And we know that since there are 3 out of 5, I can write I got 3/5 chance of getting a blue. And what about if I have a red? I have those 2 chances out of 5. Okay, now let's go on to our second draw. So once again, if we got a red, we drew a red out and then we replaced it, what we get on the second draw is it's completely not affected by what we got on the first draw. So we can still get a red outcome and we can still get a blue outcome. And similarly down here, if we got a blue first, since we replace it, that doesn't affect our second draw. So I could have a red or I could have a blue. All right, now let's go over and have a look at this. What's the chance of getting a red on my second draw? Well, since I've still got the 5 blocks in there, I've still got 2/5 of a chance. What about getting a blue? I've still got the 3/5 chance. And let's put that down here as well. Got the 3/5 for the blue and the 2/5. So now let's have a look at our sample space. I could have red, red. I can have red, blue. I can have blue, red, or I can have blue, blue. And we have those 4 outcomes. But the difference here between these and the coins, these 4 outcomes aren't equally likely because a red has a different chance of turning up as a blue. So getting a red, red or a blue, blue would have very different probabilities since there are more blues than reds. But we can use our new rule about multiplication and addition. So let's say we wanted to find the probability of getting red and a red, and I've put that there because I like using the ands. It sort of gives me a clue about what I'm going to do. Well, since they're independent events, I can do this. I can find the probability of getting a red on the first draw, which was 2/5, and the probability of getting a red on the second draw, which is 2/5, and I can multiply them together. So I've got 4 out of 25. Now, if I came over to this tree diagram here, let's see how many of those 25 outcomes would be red, red. We would have this one here. We would have this one here. We'd have this one here. We'd have this one here. What about the blues? If we start, since the first one's blue, there's nowhere down here at all that we're going to have 2 reds. So down here, there's no RR. So we have 1, 2, 3, 4. So if we count it over here, probability of getting a red and a red, 4 outcomes out of the 25. But of course, a bit tedious. Coming back over here, we've got a lot nicer tree diagram, and certainly we can use these rules that we've got. So let's have a look at another one. Let's say we wanted the probability of getting the same colours. All right, so what does that mean in our sample space? That really means that we want the probability of getting a red, red, or a blue, blue. Oh, we've got the word or coming up now. We know that or means plus, don't we? So let's go and have a look what we want here. Red, red. So we would have 2/5 times 2/5 using our AND rule. And our blue, blue. Blue, blue here. This one here. So we've got these 2 outcomes that we want. Blue, blue is 3/5 times 3/5. Let's put that down there. And if we do a little bit of math there, what do we end up with? 4 out of 25 plus 9 out of 25, and we've got 13 out of 25. There we go, and that's our independent events using our AND and our OR, our multiplication and our addition rule for probability. All right, have fun.